You'll see some of the calculations I do will be very similar to the calculations you saw this morning. But in fact, I think it doesn't hurt to see it twice, especially from two different angles. So let me remind you the Ginzburg-Landau equations. These are the time-dependent equations now in 3 dimensions. And I've taken the normal conductivity of the material to be 0, so that there's no time derivative in this equation. So there's only a time derivative in the equation for f, which is the modulus of the order parameter. So these are the equations that we want to solve, and we want to look for approximate solutions corresponding to vortex filaments in the limit that kappa is large, so that 1 over kappa is the radius of the core of the filament. So as kappa tends to infinity, these things end up being given by just curves. So I'm going to let a single vortex lie along the curve gamma, which is going to be defined by x is equal to q, and q is parameterized by s, which is arc length, and then it'll move around in time, so t is time. And I don't have any of the problems that you have in fluids in defining what this curve is, because this is just the curve which corresponds to the 0 of f. So I can define this curve very well given this equation. Okay, so you've heard me, this is the 3rd time you've heard me, so every time we do the same thing, we expand an asymptotic expansion for large kappa. So I do a power series expansion for f and for q and for h. And as we've seen already, that leads you to the result that f is just identically equal to 1 away from the vortex core. And when you substitute this into the other equations, you find you get this London equation for the magnetic field. And I said yesterday that the curl is the same as grad div minus Laplacian. And because the divergence of the magnetic field is equal to 0, I can always write this curl as minus del squared. So the equation that I get away from the vortex for the magnetic field is just minus the Laplacian of h plus h is equal to 0. So we looked at this equation yesterday for the case where there was only 1 component of h. Now we're going to look at this equation where I've got all 3 components of h in here. Okay, so that's setting the scene. So what I have to work out is what singularity does the vortex correspond to on the right-hand side of that equation. So when we were doing rectilinear vortices and I had a scalar equation, I ended up just getting a delta function on the right-hand side. I've now got to work out what's the corresponding distribution that I should put on the right-hand side of the London equation when I have a vortex filament. And to work that out, I'm first going to introduce a local coordinate system so I can describe the neighborhood of the vortex filament. And so there's lots of things that were defined this morning. I'm going to redefine them now so that you can see what my notation is. So this black curve here is the vortex filament with s increasing in this direction, s being arc length along there. And so if I take the derivative of position with respect to arc length, that gives me the tangent, so that's this vector t. And then if I look in the plane orthogonal to the filament at this point, I've got the principal normal direction, and then I've got the binormal direction. So the normal direction is given by the derivative of the tangent, and then the binormal is given by the cross product between the tangent and the normal. So this is the Serre-Frenet frame that you saw this morning. The coordinates that I want to use are effectively polar coordinates in this plane normal to the filament. So if I have a general position x, I first work out which is the closest point on the curve to that, and that defines what s is going to be. And then within this normal plane to the curve, I want to define polar coordinates, thinking of n as being sort of like the x direction and b as being like the y direction, so that I would have r cosine theta is the component in the normal direction, and r sine theta is the component in the binormal direction. So if I had a rectilinear vortex, these would just be exactly plane polar coordinates. And what you have to think of is that these are just polar coordinates in the plane which is normal to the filament. So that plane will move about as S varies. So you need three coordinates in order to describe your position. So one is the position on the curve, that's S, and then the other two are R and theta within this plane, normal to the filament at that point. So just think of them as local polar coordinates. And then, so R is the distance of the point X from the nearest point on the curve. And the advantage of those polar coordinates is I know what the local behavior of Q is now near the vortex, because the definition of having a vortex is that the phase of the order parameter looks like this local polar coordinate theta. So if I had a rectilinear vortex, I would just put chi as identically equal to theta. So locally, if I go close enough, this vortex looks rectilinear, and so locally chi is asymptotic to theta as r goes to 0. So given that this is the behavior of the phase of the order parameter locally, I know that Q is just locally like the gradient of that. And these local polar coordinates, if you work it out, as long as you're close enough, they look exactly like normal polar coordinates. So the Q is minus grad theta. That's the same as Q is minus curl of H. So locally, minus the curl of magnetic field looks like the gradient of theta, which is 1 over r in the azimuthal direction. And I can integrate that equation to find that locally H is in the tangential direction, and again, it blows up like minus the logarithm of distance from the curve. So this is sort of exactly what we did yesterday for filaments, for rectilinear vortices. The only difference is that this r and theta now are local polar coordinates, and this H was in the z direction before, and now it's in the tangent direction. So the tangent is playing the role of z, and r and theta are just playing the role of the local polar coordinates. So this is the natural generalization of what we had for rectilinear vortices. So I now have the London equation to solve for the magnetic field, for vector magnetic field, and I have this as the blow-up behavior as r goes to 0. So the London equation is valid for r positive, and this is the way that H has to blow up as I go locally. And again, you can combine this behavior into the equation by running down the generalized equation with the distribution on the right-hand side. And the distribution that you have to write is this delta function, where, so I've written it as the integral of a three-dimensional delta function over the vortex filament, over gamma, but it's a vector, and the integral is in the direction of the tangent. Okay, so H is in the direction of the tangent. That's where you get this tangent here. And the way to think of this vector delta function, the way I think about it, is that, so it's a vector. Its direction is always tangent to the curve. Its support is on the curve. And if you look in the plane normal to the curve and restrict its function to that plane, it just looks like a regular two-dimensional delta function. So in any normal plane, you've got exactly what we looked at yesterday, just a normal 2D delta function, but the direction of this vector is in the tangent direction. So this is the analog of the equation that we saw this morning for fluid filament vortices. And let me remind you, just so that I show you my notation, what that is. So for a line vortex in an incompressible, inviscid, and otherwise irrotational fluid, the vorticity is just proportional to exactly this distribution that I just introduced. So you find that the curl of the fluid velocity is, again, 2 pi times this delta function, this vector delta function, where, again, now, for a fluid, I'm allowed to have an arbitrary vortex strength, so I can put a gamma in there, whereas for a superconductor, I'm forced to have gamma is equal to 1. And then, sort of as we did yesterday, because the divergence of u is equal to 0, that tells me that I can write u as the curl of something. And so for a two-dimensional point vortex, the something is the stream function. So you write u as the curl of 0, 0 psi. Whereas, so now for two-dimensional vortices, the stream function is a scalar. If I want to write u as the curl of some potential now, then it ends up being a vector, because I'm in full 3 dimensions. So I've sort of got a vectorial stream function here, which is not the sort of thing you normally think about very often for a fluid. But I need to introduce it in order to make the analogy, because this thing is the thing which is analogous to magnetic field. So given that divergence of u is equal to 0, I can write u as the curl of this omega. I can choose the divergence of omega to be equal to 0, because writing u as the curl of omega I've got a sort of gauge invariance. Omega is only defined by this equation up to the addition of a gradient term. So I can use that gauge invariance to choose to set div omega is equal to 0. And that means that this equation here, where I have curl u is equal to this delta function, ends up being curl omega is equal to the delta function. And because I chose divergence of omega to be 0, I can always write curl as minus Laplacian. Okay, so in this, in terms of omega, the equation of a filament is just minus the Laplacian of omega is equal to this same 2 pi gamma times this vectorial delta function. So you can see exactly as it has happened in 2 dimensions, I've now got a vector stream function and a vector magnetic field, but they play the same role in the equation. So omega is playing the role of magnetic field. Instead of having, so for the superconductor, I'd have minus Laplacian of omega plus omega, or minus Laplacian of h plus h. Here I don't have the plus omega term, but that's, so the analogy is not perfect. But this is the equation that corresponds to the London equation for the superconductor. And then because u is the curl of this stream function and the electric current is the curl of magnetic field, the analogy is between fluid velocity and electric current. So that sort of natural analogy between the velocity of the electrons in a superconductor and the velocity of the fluid in the fluid. Okay, so again, so the next 2 or 3 slides are going to be a recap of what you saw this morning. So this is the Biot-Savart law that tells you if you have a vortex, what's the vortex velocity, what's the velocity of the fluid due to a vortex filament. And this just shows you how you derive that law. So the key piece of information that you need to write down to effectively I want to solve this equation. So the way I'm going to solve this equation is by using the Green's function for the Laplacian. And so the Green's function for the Laplacian, so the scalar Laplacian now, so G is a scalar, I've just got a scalar delta function on the right-hand side, is just 1 over 4 pi r, so 1 over 4 pi mod of x minus x prime. So I can solve that equation for omega just by multiplying by the Green's function and integrating. And what you find is that omega is given by, so it's the integral of the Green's function times this delta function. So x prime is the variable that I'm integrating over, and x is the variable which says where this omega is evaluated. And then if I put in my definition for this vectorial delta function, which was just this integral of the 3D delta function in the tangent direction, and then I switch the order of integration and integrate all these delta functions out, I just get an integral over the curve of 1 over 4 pi x minus x double prime. So x double prime then is positioned on the curve in the integration, and x, remember, is where this omega is evaluated. So this bit is a scalar. This is a vector. Remember, this dx prime, x double prime here is vector. This is in the direction of the tangent to the curve. So this is the familiar Biot-Savart law, where I can work out what's the stream function. If you tell me what the vortex filament is, where the curve is, you tell me what the strength is, then this integral tells me what the stream function is at any point in space. And then to get the velocity, I've got to take the curl of this thing. So you take the curl of this integral, and so you can take that inside the integral, and the dx doesn't depend on this curl. Is, remember, with respect to x, not x prime, so the only thing that depends on x in the integral is this z. So you end up, the curl of this thing ends up being the gradient of 1 over z cross dx prime. Okay, so that's the curl of a scalar times a vector, is if the vector doesn't depend on the variable x, it's just the gradient of the scalar cross the vector. And that's where this formula comes from, which is the formula that tells you what's the fluid velocity given the strength of the vortex and the curve gamma. So this is the formula that Eveline used this morning in order to work out what the fluid velocity was. So z here is just the vector which tells you the difference between x, where you're evaluating u, and x prime, which is your position on the curve, and the scalar z is just the modulus of capital Z. Okay, and the real advantage of this, so if you know what the vortex filament is, it tells you what the fluid velocity is. The real advantage is you can now evaluate this and say, well, what does the fluid velocity look like locally when I go near the vortex filament? And again, this is a calculation that we saw this morning, which is very useful for me because it means you're going to know what I'm talking about. So as the point x approaches the vortex, I expect that this fluid velocity, in terms of my local polar coordinates, should look like the strength of the vortex divided by r in the azimuthal direction. And if you do an analysis of that Biot-Savart formula, you find that that is indeed what you get, as was demonstrated this morning. And if you do a little bit more work and you evaluate more terms in that asymptotic expansion, then you find that this is just the leading term as r goes to 0. And then the next term we saw was logarithmic in r, multiplied by c as the curvature, and b as the binormal direction. And then there's some order 1 stuff. Normally, you would use kappa for curvature, but kappa is already taken for the Ginzburg-Landau parameter, so I have to use c for curvature. All right, and so I'm going to remind you of how this calculation went very briefly to see how you get this term and how you get this log times binormal term. So this is just a recap of the analysis that you saw this morning. So I want to know what's the behavior of the fluid velocity as the point at which you evaluate that velocity tends to the vortex curve. So the first thing I'm going to do is split that integral up into a local part and a non-local part. So suppose that I'm tending to the point S, where little s is equal to capital S on the curve. So that defines the nearest point to the curve, and then I'm going to let r go to 0, which means x is going to tend to q evaluated at capital S. So I'm then going to divide the integral up into 3 bits. I'm going to divide it up into the bit which is local to this point on the curve that I'm tending to, and then the 2 bits at either end, the arms. And so this was the first step that Eveline did this morning. She threw these bits away and just kept this bit. And so you've got to ask how close should you be to S in order that you get a good asymptotic approximation. So this L, the distance that you take this local bit, should be small so that I can do some expansion. So it should be much less than 1. But it shouldn't be too small. Otherwise, I'm not going to get the dominant contribution from here. I'm going to lose too much on these ends. So in fact, it wants to be much bigger than 1 over the logarithm of r. But you can choose S in this range as r goes to 0. Choose L in this range. So what we find is the major contribution to this integral, because this is sufficiently singular that it's not integrable as z goes to 0, you find that the major contribution comes from this middle bit, this local bit. Maybe I should have been a bit more careful and not put infinities here and thought about a finite vortex. But locally, the dominant contribution is from this middle bit. So I'm going to keep this middle bit, and now I've got to take advantage of the fact that L is small and effectively Taylor expand all the bits in this integrand. So the way that works, so I've got to evaluate the Q, a point on the curve, which is evaluated at little s. That's the integration variable. So I'm going to let little s be capital S, which is the point that I'm tending to, plus a little bit. And so L is going to be my new integration variable, and an R is a scale factor to make sure that I'm close to S as R goes to 0. So R is what Eveline called epsilon this morning. So when I Taylor expand this, obviously I've just got to keep differentiating, do a Taylor expansion of this Q of S plus R times L when R is small. So the first thing you get is the derivative of Q with respect to arc length multiplied by RL. So the derivative of position on the curve with respect to arc length is just the tangent. So that's why I get the first term is just RL times the tangent. And then the next term I get is the second derivative of position on the curve with respect to arc length. So that's just the derivative of the tangent with respect to arc length. And that's the curvature times the normal. So I get, from the Taylor expansion, I get RL squared over 2 times the second derivative, which is curvature times normal. So that's where this expansion comes from. This is the distance between the point on the curve defined at little s and my point x. So my point x, remember, was given by r. Its distance from q of s is r cos theta in the n direction and r sine theta in the b direction. So that tells me how far away I am from q, but to work out how far away I am from this bit, I've then got to subtract all this. So that's why you get here an r cos theta minus this r squared L squared c over 2 in the n direction. You get an r sine theta in the b direction, and then you get minus this bit here as well. So that's how you just work out what z is. That's the vector that takes you from your point x to this point q of r plus s plus r times L. And then finally, I've got to expand this ds at the end, so that involves expanding the tangent, but we've just seen how to do that. So Taylor expand this, you get the tangent evaluated at s, and then you get RL times curvature times normal. So these are exactly the same 3 expansions that Eveline did this morning. And you stick all these into this and expand this integrand here, and you find that these are the terms that you get from that. So let me show you where they come from. So this first term is in the azimuthal directions, in the e theta direction. And that comes from these terms here. So you can think I've got an r cos theta n and an r sine theta b. So that's really a vector which is in the radial direction as far as my local polar coordinates are concerned. So when I take the radial direction and I cross it with the tangent, which is so I've got the radial direction, I cross it with the tangent, I get an azimuthal vector. And that's where this guy is coming from. And then this b is coming from the rest of this stuff. So the first term you get has got, you've got an integral that is finite, so you can let r tend to 0 in this bit, and you get a 1 over r singularity. Then you get this bit in the binormal direction. This is the bit that gives you the logarithm. You've got an L squared on the top and an L cubed on the bottom as L is large. And so you get a log r coming from this. And then you get some other stuff which is finite but not especially nice. You get an e theta, again some more azimuthal stuff with the cos theta and a finite integral. So when you put it all together, this local bit, so this is just the same thing written again, this local bit, when you evaluate all that, this is where you can do all these integrals exactly, and this is what you get. And so when you evaluate this at these limits, you get a log of L over R coming out of that. But the answer shouldn't depend on L, because I'm trying to asymptotically approximate this integral, and L was sort of an arbitrary region which I said was going to dominate. So the answer shouldn't depend on what L is. And in fact, it doesn't, because you can show that the sort of artificially introduced log L singularity that you get from the local bit cancels with the log L singularity you get from the arms of the bit that you didn't include. So when you work out the limit of this bit due to the arms, you find that it's finite as L goes to 0. So this is the local expansion of the fluid velocity. So now comes to the law of motion. There's quite a discussion on this morning. So the first term that you get in this expansion is the gamma over r in the azimuthal direction. So that is just the vortex doing its stuff where the fluid is circulating around the core, and it does not cause any translation. That's the same term you would have for an isolated rectilinear vortex. It's the next term in the expansion that is going to cause it to move. So the next term is minus log r times curvature in the binormal direction. And we're supposed to evaluate this at r is equal to 0, so we're going to get infinite velocity for the vortex in the binormal direction. So there was some discussion about how you can do this. So my take on that is that these equations with the delta function in are not valid when you get into the vortex core, that we think of the vortex as either being a little patch of vorticity of finite radius, and then I'm thinking of the radius being small, or you could even think, well, if I've really got the Navier-Stokes equations, then when I've got velocities and gradients of velocity that are getting very large when I get towards the vortex core, so I really can't neglect viscous terms when I've got very large gradients. So there's some regularizing mechanism for this delta function when you get close to the core of the filament. And so it's either a smoothed out vorticity or it's a little bit of viscosity. And so when you introduce that regularizing mechanism, that gives you a small but finite core radius. And that effectively, when you do the matching between your inner solution where you see the smoothed out regularized core and this outer solution where it appears singular, then instead of getting log evaluated at 0, you end up just picking up a log of the core radius. And so the velocity is large but finite. It has a log of epsilon in there. And so I've got this log of epsilon in the binormal direction, and then I've got some regular part, which is everything else. So this stuff could be the velocity due to images. It could be it's the velocity due to the arms of the vortex that give me a finite thing. Or it's the velocity due to any other vortices that happen to be around. So I've got the local bit, and then I've sort of got the global bit due to everything else. And if you just retain this bit and just have a local velocity law, as Evelyn said, that's known as the local induction approximation. So that works providing log epsilon is large enough. Okay, so that's just to remind you what you learned about this morning. The reason for showing you that is that I want to do the same procedure for superconductors now. I want to see if I can work out, all right, what's the local electric current as I go near a vortex filament, and do I have an analog of the Biot-Savart law? Can I work out what the velocity of a superconducting filament is? And so we've seen that the analogy is between magnetic field and vector stream function, or between current and fluid velocity. And then I've just got to remember that I don't have any gamma for superconductors, that the strength of the vortex is always equal to 1. Okay, so what's the analog of the Biot-Savart law? So I've got, instead of Laplace's equation, I have a modified Helmholtz equation. I had the London equation for magnetic field. So instead of looking for the Green's function for the Laplacian, I have to look for the Green's function for the modified Helmholtz equation. But fortunately, that's another equation that has a very nice Green's function 3D. So this Green's function, instead of being just 1 over 4 pi r, it's e to the minus r over 4 pi r, another very well-known Green function. So once I've got that, I can just do the same thing. I multiply the equation by this Green's function integrate, then I write out what's the definition of my distribution, this vectorial delta function. Then I switch the order of integration, and I can do the integral, pick up just an integral along the curve because of the three delta functions. And I find the magnetic field is just given by this simple integral here. So this is my analog of the Biot-Savart law, that I have the magnetic field is just the integral over the vortex curve of e to the minus z over z, where z is the distance from the point on the curve to the point where you're evaluating your magnetic field. So for a fluid, remember this was gamma over 2, so I had a gamma at a vortex strength out the front, and then the Green's function was just 1 over z. So the difference is only this e to the minus z on the top there. And once I've got magnetic field, I can work out what the current is by taking the curl. So this is the analog of the fluid velocity. So you take the curl of this, and exactly as before, the only thing in this integral that depends on x is z. So I just get the gradient of this e to the minus z over z cross the dx prime. And then I can evaluate this gradient. I would get two terms here. So for a fluid, you would only have this last term here. And it wouldn't have the e to the minus z. But I have a formula which is not identical, but it's exactly analogous to the Biot-Savart law for a fluid vortex. Okay, so what's the program? So first of all, I get the Biot-Savart law. Then I want to say, all right, so what's the asymptotic behavior of Q and H as I let my point tend to the vortex? So I've got the same local polar coordinates, and I know that Q, looks like minus 1 over r e theta locally. And so that tells me that the current, that Q is minus curl of H, so this is the current, remember, is analogous to the vortex velocity, the fluid velocity, so that I had U as 1 over r e theta. Here I've just got J as 1 over r e theta. But I can do the asymptotic procedure of the expansion of the Biot-Savart law exactly the same way for this new Biot-Savart law. And in fact, I'm not going to show you because it works out exactly the same. The only difference between this and the corresponding thing for a fluid, well, so it's the e to the minus z. So remember, I'm doing this as z goes to 0. It's the asymptotic expansion as z gets small. So for small z, this term doesn't give you anything. It's all in this term because it's got a z cubed on the bottom, and this one's got a z squared. So this is the dominant term. And the only difference between this and the fluid is I've got an e to the minus z on the top. But when z tends to 0, e to the minus z tends to 1. And so this term, the singular parts of the local expansion are identical for a superconductor and for a fluid. It makes no difference because the difference is the e to the minus z. And so I still, if I follow the procedure, I get exactly the same local expansion for Q. So I still get Q is minus 1 over r e theta. Then there's a log r term multiplied by the curvature in the binormal direction. And then there's all the order 1 stuff. So it's exactly the same asymptotic expansion. We've been able to transfer all that technology across from fluids. So then the question comes, all right, how does the vortex move then? What's the response to that local behavior? So we saw for rectilinear vortices that if the local behavior of Q was minus 1 over r e theta, that's the thing that defines there being a vortex, plus a c was the next term, then we saw that the velocity of the vortex was proportional to this c. The proportionality constant was beta that we could calculate, but it was rotated by pi over 2 for rectilinear vortices. So it wasn't in the direction of c, it was rotated. So you can do a very similar analysis for a full 3-dimensional vortex where you go into local curvilinear coordinates to look at what the core looks like. But in order to generalize this law, I sort of got to this perpendicular thing only works in 2 dimensions. I've got to work out what's the sort of coordinate-free way to describe rotating a vector by pi over 2. And so the way to think about that is that, well, if you have a vector in a plane, rotation by pi over 2 is really just the cross product with the normal to the plane. So if I take a cross product with the normal to the plane of c, then that effectively just rotates the c by pi over 2. And so this law of motion here just really says that the velocity is not in the direction of c, it's in the direction of the tangent cross c. And that's the law which generalizes to 3 dimensions. And so when you do this local analysis, what you find is that the velocity is not in this direction. It's not in the b direction, but it's in the t cross b direction. You've got to take the cross product between the tangent and the binormal. And what that means is that the motion of a superconducting vortex is not in the binormal direction, but it's in the normal direction. And all this discussion of, well, what about the infinity because as r goes to 0, log r blows up, I already have a regularization of my vortex filament because I started off with the Ginzburg-Landau equations. And so the Ginzburg-Landau equations exactly do that regularization. And because the rescaling when you go and you see the core of the vortex happens when r gets to be order 1 over kappa, that means that the size of the velocity ends up being not log of 0, but log of kappa. And so that gives you automatically gives you a cutoff when you do this inner and outer matching. So I've got a velocity law which says velocity is proportional to curvature. It's large, like the logarithm of kappa, and it's in the normal direction, not the binormal direction. And that's the local induction approximation. Then I've also got the law that I would get due to everything else. So there's a sort of regular part of Q as well, which, as I say, would include the arms of this particular vortex. It might include any other vortices. It might include fields due to boundaries or images. Okay, so that's given you the analogy between what fluid vortices do. You can follow exactly the same procedure and find out a lot about how superconducting vortices work. Before I show you some examples of motion and contrast the motion of fluids to superconductors, I just want to interpret this velocity law for you. So we find that the velocity is t cross q. So why do you get t cross q? What does that mean? Or how would a physicist interpret that? And so I want to recall that q is, the London equation tells you curl q plus q is equal to 0. So q is minus curl q, and curl q is equal to h. So q is minus curl h. And curl h is equal to current, so that tells me that q is minus j. So this law of motion, I could rewrite it as the velocity. I'd get a minus j, so let me switch the order so I don't have a minus sign. So the velocity is j cross t. So you take the electric current and you cross it with the tangent. So for a fluid, the velocity would just be in the direction of u. J is playing the role of u, but I've got to take this cross product with tangent before I work out the direction of velocity. So what's the interpretation of j cross t? Well, if you remember, the vortex is carrying a quantized amount of magnetic field, and that magnetic field is in the tangent direction. So saying v is equal to j cross t is like saying v is equal to j cross h. Because t is in the direction of h, and there's a quantized amount here, so I just have to put a proportionality in there. So j cross h is something that is quite familiar in electromagnetism. So that's the Lorentz force. If I have a wire carrying a current j, and I put that wire into a magnetic field, then of strength h, then the wire would feel a force, and the force would be proportional to the current, it would be proportional to the field, and it would be in the direction of the j cross h, and it would cause the wire to move. This is how electric motors work, for example. And so one interpretation of this law of motion is that this j cross h is giving you a Lorentz force on the vortex. So that's sort of backwards way around. So you normally think, all right, I've got a wire carrying a current, I put it in a magnetic field, so it's the thing which is carrying the current which gets the force on it. Whereas here, it's the thing which is carrying the magnetic field which is going to move and get the force on it. So it's sort of backward way around to normal. But that's one interpretation, is that J cross H is the force on this magnetic field line. And then when you say, well, all right, force, you think of an overdamped system where instead of force being proportional to acceleration, you have force as proportional to velocity. So you think about some viscous dissipation as the vortex moves, and you come up with a law that says that the velocity of the vortex should be equal to J cross H. And this is the physics interpretation of what this velocity law means. Okay, so I'm going to write the law in terms of J instead of Q, thinking of J as being the primary physical variable. So that tells me that the velocity of the vortex is in the normal direction proportional to curvature, and then there's a J cross T, where J is the regular part of the current. And in fact, by rescaling time, I don't really care what this mobility is, because the only thing that depends on time is this velocity. So if I measure units of time, measure time in units of 1 over beta, I can rescale this and get rid of the beta out of the equation just to tidy it up a little bit. All right, so what do solutions to the equations look like? So Eveline showed you a few this morning. The simplest is a vortex ring. So if you have a vortex ring, it's constant curvature, so a fluid vortex would move in the binormal direction, which is the normal to the plane of the ring. So the radius would remain constant, and you would have uniform translation. So for a superconducting vortex, the motion is not in the binormal direction, but it's in the normal direction. If the radius is constant initially, so if it's a circle, then it remains a circle because the velocity at every point is the same in magnitude. But because the direction of the velocity is in the normal direction, what you find is that the circle shrinks. So a superconducting ring, if you've got motion by curvature, a circle will tend to a point in finite time, in fact, because as the circle shrinks, the curvature goes up, the velocity goes up, and it collapses in finite time. But you will have no translation, so it stays in the plane that it is in initially. And the other simple solution to the equations is a helix. So if you have a helix in a fluid, you find that it rotates and it translates. So of course, it's hard to, you can't tell the difference between those two as far as just the curve goes, but it looks like the curve translates along the axis, but you have a constant pitch and you have a constant amplitude. Okay, so the distance between successive loops is constant, and the radius, the amplitude of this helix, is constant. If you move in the normal direction, so for a superconductor, you have no translation, you have still a constant pitch, you don't have any rotation, but you have an amplitude which decays to 0. And so the helix basically straightens into a line, but this time it takes infinite time, because as it straightens, the curvature goes down, not up. So it takes infinite time for this to straighten. So superconducting vortices act a little bit like they've got a line tension. So if you had a filament with tension, it would want to straighten, and the force would be proportional to the curvature. The more curve, the more force. So that's a way to have a bit of intuition about how a superconducting line vortex is going to behave. It wants to reduce its length. Okay, so when we followed this procedure through for vortices in 2 dimensions, we had point vortices, and we took the Ginzburg-Landau equations, and we took the limit in which the vortices became singularities. I had linear equations, so I could add up the contributions from different singularities, could work out how they move, and then the next step was to say, all right, well, maybe I don't want to keep track of millions of individual vortices. Can I write down a model for a vortex density or a vorticity, which I would have, for example, analogous to the Euler equations? So that's the stage we've got to for these 3-dimensional vortices now. We've got vortex filaments. We can track their motion. Can we derive a 3-dimensional analog of the vortex density equations that I wrote down before? Can we have a 3-dimensional version of the Euler equations? And So in order to motivate how you would do that, I'm going to see if I can do it for fluids first. So suppose I took a collection of vortex filaments in a fluid. How would I get back from vortex filaments to the Euler equations? And if that works, given I know what equations I'm hoping to find, then I can follow the same procedure for a superconductor, and I'll have some trust in the equations that I end up with. So I'm going to do this very formally. The system of vortices that I have, again, it's linear equations, so I can just add lots of these vortex filaments on the right-hand side. And I have to make some assumption that this limit is well defined, that these filaments locally are in the same direction. But if I follow the same sort of averaging procedure that we did yesterday, and I integrate over a small ball and let the separation between vortices tend to 0 and let the size of the ball tend to 0, and let the strength of the vortex tend to 0 in such a way that gamma over d squared is finite, where d is the typical vortex separation. So the same limiting procedure we did yesterday. Then you can convince yourself that this sum of delta functions is going to end up becoming this vorticity, so that you get back from isolated filaments into a vorticity. So exactly as we have found for point vortices, I've introduced another variable, but I don't have any more equations. So I've now got one equation that's got two unknowns in it. And so I'm missing an equation. This is not enough now to solve for u and omega. And the equation that I'm missing is the equation that describes vortex conservation. So when I'm keeping track of individual vortices, I'm not going to lose any. As soon as I smear them out into a density, I've got to add back in the equation of vortex conservation, vorticity conservation. And what we did in 2D was just say, all right, take a little blob, look at all the points inside it, all the point vortices inside it, and convect it around with the fluid with the same velocity as the fluid has, and then no points can come in or out, and that's the way you define your conservation law. Now, if you had points in 3 dimensions, you'd do the same thing. So if I was trying to find conservation of point charges, for example, I'd take a little blob, and I would convect it around, and I'd say that nothing can come in or out. But I don't have points, I have lines. So it's a little bit more unusual to do this conservation equation for lines. And the way that you do it is you imagine still that you have a surface. So I have some little patch, I've got some curve in 3D, which is bounding a little surface S, which is an open surface. And then I look at all the filaments which intersect that surface. And then just to make it really clear, I can even put the tube around them all. And then if I convect this tube and this surface with the same velocity field that the filaments are being convected with, then I'm not going to get any vortices going in or out of the tube. So the number of vortices in the tube is going to be constant. So that tells me my conservation law is the integral of these delta functions dot the normal to this surface counts how many of these vortices cross this S. So the convective derivative of that integral should be 0. And that says that nothing comes in or nothing goes out. So that when you do this homogenization, this formal averaging procedure, the conservation law that you get is the convective derivative of the integral of omega dot n over any surface advected with the same velocity as the vortices should be equal to 0. And then since S was arbitrary, there's an equivalent differential form. You can take this d by dt inside, and you find that this time the differential form of this conservation equation is the time derivative, this time derivative of omega plus the curl of omega cross v is equal to 0, where v is the velocity with which these things are advected. So the last thing to close the model is to say, right, what is the velocity with which all these filaments are advected? So this is why I've now got to go back to this local velocity law, I've got this local induction approximation, which has, so I'll put a kappa in there. You think of that as being an epsilon for a fluid, in the binormal direction. And then I've got the regular part of the fluid velocity. So if you just got one vortex, then this guy is bigger than this because of the log kappa. But if I got lots of vortices and they're very close together, then this guy is of order gamma over d squared, whereas this guy is of order gamma log kappa. So if the density gets so big that 1 over d squared is much bigger than log kappa, then the motion of each vortex is dominated by the mean field and not by the self-induced motion. So if you take the limit as d goes to 0 and such that this inequality holds, then the velocity of the vortex is just the mean field, which is the same as the velocity of the fluid. So that tells you, that's how you get back to vortices being advected with the fluid. So that finally gets you back to the Euler equations. So this is the full three-dimensional Euler equation. Vorticity is equal to curl of u, divergence of u is equal to 0, and this vortex conservation law. This is a way to write the Euler equations. The way you may be more used to writing them is, so if I substitute for omega in here, that would be the curl of du by dt. So then I've got two curls, so I can integrate. So I get du by dt plus omega cross u is the gradient of something, which is the pressure. So that's the way you would normally see it. Okay, so subject to a little bit of hand-waving and a little bit of hoping, I've managed to get back to the Euler equations. So I can follow the same procedure in the superconducting case and have a look to see what we end up with. And so as we found in 2D, I'm not allowed to let the strength of the vortex go to 0. But that just means that I have to rescale my magnetic field and my vorticity with 1 over d squared to keep everything finite in the limit. So if I do that, then this is the London equation with the collection of vortices on the right-hand side. So you do the formal averaging procedure, and you're going to replace this collection of filaments with a continuous vorticity. And then the divergence of H that goes through, nothing happens to that. The conservation of vortex filaments, well, that argument, I didn't have to tell you anywhere that they were fluid vortices. I just had to tell you they were lines that were advected with a certain velocity. So that argument is exactly the same, whether I'm dealing with fluids or superconductors. So the conservation law is exactly the same. And then when we go to the law of motion, I have to say, what is this V? So again, I'm going to use the same argument and say, well, providing the density of filaments is sufficiently high, the local induction approximation, the local behavior is going to be negligible by comparison to the mean field. So I have no self-induced motion. I'm just going to include the mean field motion. So that tells me the velocity with which they're advected is, so it's j cross the tangent. So what's the tangent? Well, so that's the direction of the vorticity divided by its modulus. So this is the velocity law, where j is curl h. There's an interesting interpretation of, so vortex conservation, so for Euler, I showed you how to get just from vortex conservation back to Newton effectively by integrating the curl. You can ask here, what does this equation mean in terms of, in superconductors, why do I get it? One interpretation is that if you work out what the electric field is, you find you get 2 bits. You get one bit where E is dj by dt. And in fact, this was one of the early equations written down for superconductivity. So if I have a normal conductor, then I would find E is proportional to J. That's just Ohm's law. So if you apply an electric field, you get an electric current. And you sort of think of that as the electric field is pushing the electrons, but the electrons keep bashing into stuff. So you've got to keep pushing in order just to maintain their velocity. So it's a sort of a viscous dissipation, if you like. Force is equal to velocity. Whereas in a superconductor, there is no resistance. So you keep pushing the electrons, they go faster and faster. So you sort of get force is equal to acceleration instead of velocity. So this is a term that says if you apply an electric field to a superconductor, you keep getting bigger and bigger currents. It's dj by dt. This is acceleration is equal to electric field, not just velocity is equal to electric field. And then the second term is effectively a moving magnetic field causes an electric field. So remember, the vortices are carrying magnetic field. If you move them with a velocity v, then you've got a moving magnetic field that generates an electric field. And it would be in a direction which is perpendicular to the magnetic field and perpendicular to the direction of motion. So this is the electric field generated by moving vortices. So that's what the total electric field is. And then, given this expression, if you can rewrite this equation and you just get curl of E plus dH by dt is equal to 0, which is rather reassuring because that's Faraday's law. And so that's one of Maxwell's equations comes out once you know what the electric field is. You could say it's a circular argument because this is why a moving magnetic field generates an electric field, so it's sort of built in here with this omega cross V. But at least everything is self-consistent. Okay, so here's the summary. I've got Euler equations on this side written in terms of this vector stream function that I introduced and the vorticity and the fluid velocity. And I've got this new analog of the Euler equations for three-dimensional vortex filaments in a superconductor for the magnetic field, the vortex density, and the vortex velocity. And you can see that they're sort of similar. So H is obviously analogous to omega, capital omega. The vortex density is analogous to the vorticity. I get this extra term plus H here that we've seen a few times. And I get this rotation of the velocity here. So here V is equal to curl of omega. Here V is curl H cross the tangent. So cross omega over mod omega. So I've got two terms which are different between the sets of equations. This rotation of the velocity is actually quite important. We've already seen that it leads to like vortices repelling each other. It leads to a single filament wanting to shorten its length. And it's sort of, it means the motion is dissipative rather than conservative. So it leads to diffusive type behavior. Things want to get as far away from each other as possible. And then this decay of magnetic field away from vorticity is exponential rather than algebraic. And as I said yesterday, that means whenever you've got an exponential, you've got a length scale. And so this means that whereas these equations are scale invariant, there's no natural length scale for a fluid. You get the same equations whether you're in a teacup or whether you're on the scale of the atmosphere. The same is not true of a superconductor, and that these equations are written on the length scale of the penetration depth. So we can do the same thing as we did yesterday and say, all right, so the penetration depth is small. What happens if I've got a big sample? What happens if my superconductor is much bigger than this penetration depth lambda? So in that case, what you would want to do is to rescale your equations so that instead of using the penetration depth as your length scale, you use the sample size as your length scale. And if you do that, then you end up introducing a parameter into the equations. You get this ratio of your penetration depth to sample size appears in front of this second derivative of H. And again, as I said, lambda is typically about 0.1 microns. So if your sample is a lab-sized sample, even on the millimeter size, this epsilon is going to be very small. And so to leading order, apart from in boundary layers, that's going to tell you that H is equal to omega. And if you put H is equal to omega and you sort of combine all these equations together, then you can write down a single equation for H, which is a vector equation which has got, well, it's got 4 cross products in it. It's a curl of H cross curl of H cross. So it's got 4 cross products in there. So it's sort of hard to see what sort of equation that is. But if you remember, in 2 dimensions, this reduces down to this nonlinear diffusion equation. So I think it's some vectorial version of this nonlinear diffusion. There's one thing that I could have mentioned yesterday that I didn't, and that is another effect that's due to this rescaling onto the sample size. And so when I rescale and I say I'm going to now scale length with sample size, implicitly when I cross that epsilon, when I cross this epsilon times the second derivative out here, I'm implicitly assuming that h is not varying very rapidly. So I'm assuming that the derivative of h is not large and epsilon is small, and so this term together is small. And that's a sort of natural assumption that if you have a sample of size 1, you'd expect h to vary on a length scale of order 1. But the thing is that if h is varying on the sample length scale, due to whatever I've applied, in terms of boundary conditions, then the electric current is the curl of h. And so when I take the curl, that involves a derivative. And originally that derivative was with respect to a length scale which was lambda, and now it's with respect to a length scale which is a sample size L. And so the curl of h, if h varies on the sample size, ends up being scaled by a factor of epsilon. So that tells me the electric current is a factor of epsilon smaller than it was when I derived the equations. And that tells me, if I go back to when I did the mean field limit, I said, well, the current due to all the neighbors is 1 over d squared, and the current due to the mean field is 1 over d squared, and the current due to the nearest neighbor is 1 over d. Whereas now, the current due to the mean field is epsilon over d squared, and the current due to the nearest neighbor is 1 over d. So now it's not so clear whether epsilon over d squared beats 1 over d or not. And in fact, it only beats it only dominates if d is much less than epsilon. And what that tells you is, so d is much less than, so those are both non-dimensional, so what is that dimensionally? That tells me that the dimensional vortex separation, in order for the mean field to work, should be much less than lambda squared over L. So it gives you a limit on what the size of the vorticity has to be in order for mean field forces to dominate. And I think that this cutoff is to do with what they call vortex lattice melting. So that quite often you see pictures of vortices and superconductors, and you see this nice regular hexagonal grid of vortices. I showed you a picture on Wednesday. And that's the sort of thing you get when local forces dominate. That if your local nearest neighbors are telling you you want to be as far away from them as possible, then you form a nice hexagonal lattice. Whereas most of the discussion that we've been having, I've been imagining vortices freely moving and responding to the bulk electric current. And so you have this distinction between a vortex liquid, where the vortices are responding to the mean field and everybody is moving along together quite happily, and a vortex lattice, where everybody gets locked down and you don't want to get too close to any of your neighbors and the local forces dominate. And so if you're in a strong lattice locally, if you want to get any bulk motion, you've got to do that through dislocations in the lattice and things like that. And this seems to be the cutoff between this density of vortices that you need. This tells you whether our local force is going to dominate or our global forces, our mean field force is going to dominate. So am I going to get a liquid or am I going to get a lattice? Okay, so there's just one last calculation that I want to show you. And it's a sort of spanner in the works, if you like. So I've been going along saying you have this nice analogy between these, and I can write down these equations, and they look a little bit like Euler, and aren't they very good? But in fact, this rotation of this velocity law causes a little bit of trouble. And so what I did when I went to the mean field, I threw away the local part, I threw away the self-induced motion, and I just said that the vortex is responding to whatever the mean field current is. And so now what I want to go back and do is to say, well, so suppose I have a vortex and I throw away its local part and I just say, everybody else is generating some current. What's the vortex going to do in response to that current? So I want to impose a current, which I think of as being due to everybody else, due to the mean field. And I want to see what does my one filament do in response to that current. So I want to just have a look a bit more carefully at this velocity law that I wrote down, where I only kept the mean field part and I threw away the local part. Because this velocity law is not actually very nice. And so to analyze this, I'm going to look at I want to do a stability calculation. So the goal is to show you that actually, if you've got this sort of velocity law, then your vortices are not going to stay all nicely lined up in the same direction. There's an instability that's going to kick in, and that's going to affect your mean field model and cast a bit of doubt on my hand waving. So I'm going to do it for a rectilinear vortex. I'm going to suppose that I have a vortex that's just in the z direction. So if it's in the z direction, I can parameterize it. So S, which was arc length, can now just be z. So my vortex is given by curve Q, parameterized just by z, and then I've got the position of the vortex in the plane is just given by x and y, and those will only be functions of time. Okay, so this is my Q of z and t is just x of t, y of t, and then z. So the tangent is just in the z direction. The velocity is in the plane, and it's x dot, y dot, so dot is d by dt. And so this velocity j cross t just gives you it's the perpendicular, it's the rotation of the first two components. So it gives you j2 minus j1, then 0. So this law of motion, when I equate velocity to j cross t, just tells me that x dot is j2 and y dot is minus j1. So if j is constant uniform external current, then this is just going to give me a uniform translation. So x is just going to be linear in time with proportionality j2, and y is just minus j1 of t. So this velocity law, as we expect, just gives me a uniform translation in an external current. So the analogy for a fluid would be if I have a uniform velocity field and I put a vortex in it, the vortex just gets advected with that velocity field. So what's happening here is exactly the same thing, apart from it's not going with j, it's going orthogonal to j. So now what I want to do is say, all right, that's the motion I sort of assumed when I wrote down the mean field model. Is that motion stable or not? So what happens if I take that solution to the rectilinear vortex and I give it a perturbation, and I look to see how does the perturbation evolve? So this is my base state. It's the uniformly translating vortex. And now I give a perturbation, which is small, where smallness is measured by this parameter epsilon. So now I have to work out what's the new tangent, what's the new velocity, what's the new j cross t, with this being the position of the vortex. So when you do that, well, you can find what the tangent is. You still get a 1 in the third component from this term, and now I get the derivatives of these two guys with respect to z in the first two components. You can work out what the velocity is just by differentiating this expression with respect to time, and it just gives you this. And then you can do j cross t, and when you do that cross product, that's what you get there. I don't expect you to read it now, but I wrote it down so that it's there when you go and look at it later. All right, but so you equate this to this, and you find the law of motion. And so I can just pick off only the first two components matter, because any motion along the axis, along the tangent to the vortex doesn't do anything. It just changes the parameterization. So to a first approximation, I know that the j2 terms cancel, because that's how and the minus j1 here cancels with the minus j1 there, because that's how I set up my uniformly translating vortex in the first place. So now I've got to look at the epsilon terms and balance those. And what I find is I get xt here is minus j3yz there, and yt here is minus j2xz here. No, here. That's it, j3xz. So I get an equation, I get a pair of equations for x and y. And, yeah, so same two equations. So if my initial, I didn't give any initial conditions yet, so suppose I give an initial Fourier series mode, I give initial sine kz for x, then, well, the form of these equations says that you should give sine kz for x and cos kz for y. And these are linear constant coefficient equations, so the solutions are going to be exponential. So I have an e to the mu t, where mu is the growth rate of this perturbation. So if it's going to be stable, I want the real part of mu to be negative. If I find the real part of mu is positive, it's unstable. And when you work it out, what you find is the solution to this equation gives you mu is equal to plus or minus k times J3. So once I've got plus or minus, it doesn't matter whether J3 is positive or negative, or k is positive or negative. I'm always going to have one stable mode and one unstable mode. And with x being sine kz and y being cos kz, so they're going around a circle as z increases. So that means this is a helix now. As z increases, x and y go around a circle. So this is the helical instability of a uniformly translating vortex, which happens whenever J3 is non-zero. So J3 is the component of the current which is along the line of the vortex. So if there's any current which is in the tangent direction, then you get this, this instability. And in fact, it's worse than instability. It means the law that I wrote down is actually ill-posed, because the growth rate here tends to infinity as k goes to infinity. So small wavelength modes grow arbitrarily quickly. So all the 2D stuff we did, we were all right, because the current was in the plane, so there was no J3. But as soon as you have a component of current which is in the direction of the vortex, then you have this catastrophic instability. And the reason is, well, you can think of it, suppose I say I've only got current in the direction of the vortex. So suppose my filament is in the z direction and the current is also in the z direction. Then that vortex wouldn't move, because J cross T is equal to 0. But if I give any little perturbation to the vortex, then I change what the tangent is. And then suddenly J cross T is not 0 anymore, and it's going to move. And that's what's causing this instability. It's that it wouldn't happen for a fluid because you didn't do this cross product. But it's the cross product means that you can have something which is not there, and you perturb, you can give an infinitesimal perturbation to the vortex, which can change the normal by a lot. And that's what's happening. So what this means is that so the mean field model that I wrote down actually exhibits this instability as well and is ill-posed. So, it's not clear whether it's still ill-posed if you do the nonlinear diffusion case, because you've taken another limit there, so I don't know whether anybody's looked at that. But certainly it's been shown that the vortex density model exhibits this instability. So one way to salvage the situation would be to say, well, all right, that happened because I threw away the self-induced part of the law of motion, which was proportional to curvature, so it's going to stop anything getting too bad. So you can do the same analysis where you include the full law of motion. So instead of just having J cross T, you include the curvature times normal term. And so I'm just tidy it up and let all this stuff here just be equal to this nu. So I took the limit before that d was much smaller than the square root of 1 over log kappa. So that this nu, I took the limit in which nu went to 0. But maybe if I keep nu in, let's see what happens. So the analysis goes in a similar way. You just got this extra curvature term to work out. But because we're perturbing about a rectilinear vortex, that just ends up being the second derivative of the perturbation. And so when you do the law of motion, this is what I had before. You get this extra curvature times normal, so curvature times this nu. And so you get these extra two equations on the right-hand side here, the extra two terms in these equations, where you have an xzz times nu in the x equation and a yzz times nu in the y equation. And that's enough to stop the high modes being unstable. So here are the two equations. They're still constant coefficient linear equations, So you can do the same sort of Fourier series analysis. So if I look for the same Fourier mode, you find you substitute that into the equations, and you get the system of equations for the coefficients. So it's the usual thing that you get a homogeneous system for A and B. You want to have non-trivial solutions, so the determinant had to be 0. So the condition for a non-trivial solution gives you the relationship between the growth rate mu and the wave number k. So this is the dispersion relation. And this time, so plus or minus k times J3 is what we had before. This extra curvature term, as you might have anticipated, gives me a minus k squared times nu. So this extra term is stabilizing. And in particular, it means that as k goes to infinity, mu is negative now. So the large wave numbers have been stabilized, so the small wavelengths have been stabilized. And what that means is that the growth rate is now bounded rather than being unbounded. So it's still unstable. There are always values of k which give you positive value of mu, but there's a maximum value of mu. And so it's not ill-posed, it's just unstable. So you find there's a band of unstable wave numbers, which is the modulus of k less than J3 over nu. So one way to regularize this mean field model and cope with this instability would be to include the self-induced curvature term in there. So it makes it a little bit messier, but one thing you could do is to, instead of just having so this is the J cross T term that we had, you could add in the curvature times normal, and that would be a term like this. So why is that true? So curvature times normal is the derivative of the tangent with respect to arc length. So what's the direction of arc length? Well, that's the tangential direction, so that's T dot grad of T. And then T is like omega over mod omega. So that's why you get omega over mod omega dot grad of omega over mod omega. So you get sort of slightly nasty thing inside the velocity law here, but this is going to stop the high wave numbers being unstable. As I say, it's not clear whether once you take the limit to nonlinear diffusion, you still need to do something like this or not. Okay, I'm hitting my summary slide. This is the procedure that we've sort of looked at. So the fundamental equation that we started off with, the gold standard, if you like, was the Ginzburg-Landau model. That's the equation that we're trying to approximate solutions of. If we take the limit in which the Ginzburg-Landau parameter kappa tends to infinity, then that means that I get this separation of length scales so that the core of a vortex becomes much smaller than the length scale for the decay of magnetic field away from a vortex. And in that case, the vortices become line singularities. So I ended up with the London model, which is a linear equation, but with vortices now as isolated line singularities. And then what we did was we said, well, suppose we've got a lot of them, and we let the separation tend to 0, and we do a formal homogenization, so then you can get to a model which is a vortex density model or a model for a vorticity. And then because I still got this length scale in the problem, which is the penetration depth, you can also take the limit in which the penetration depth is small by comparison to the size of your sample, in which case even this model reduces and you end up with some sort of nonlinear diffusion equation. So you have this hierarchy of models on different length scales. So here you would be interested on the length scale of a vortex core, if you like. This is on the length scale of a few vortices. This is many vortices, and then this is when you're much bigger than the penetration depth. And then this is the final slide that shows the analogy between superconductors and fluids. So most of the courses this week have been drawing the analogy at this level. So we've had the Euler equations with vortices as line singularities, and that's fairly close to the London model again with vortices as line singularities. And the regularization that I have on the superconducting side is I've got the Ginzburg-Landau equation, which tells me, all right, here I've got a line singularity. How do I regularize that? What happens when I go and really look at the vortex core? And I've got the nice Ginzburg-Landau model sitting there underneath, which describes what's the structure of the vortex core, and I've been able to work out how vortices move and all sorts of things from it. With fluids, then you have to work a little bit harder to work out, how you're going to regularize this vortex core, and it sort of depends what you want to do. You can either have a little patch of vorticity, or you could do sort of full Navier-Stokes and say, well, the velocity gradients are so large that I've got to worry about viscosity in the core. And then on the fluid side, it's very natural that you think of line vortices as being an approximation to a distributed vorticity, and you have the Euler equations. And so we've taken advantage of the analogy to say, well, can we do the same thing over here? Can we write down equations that have got a distributed vorticity or a vortex density, even in the superconducting case? And we found that we've got these vortex density equations, which look a little bit like the Euler equations. But I've just sort of highlighted that there are one or two things that are not so pretty about them. So it may not be... a lot of this system has been easier than this system, but it may be when you get to this stage, there are some sort of skeletons in the closet there. Okay, and I think that's all I want to say, so thank you for your attention.